in-class example. So I just want to do a video of our in-class example, which was a beam calculation. So it's a 3-ply built-up wood beam for a 24 by 40 bungalow. So it's the exact same one we did in class for our example. I just figured it would be handy for assignments, studying for tests and stuff like that. So here we go. So we're just going to start working through these over here. So A, airspace at the end of a beam. Right, so if you look at the drawing here, it's pointing to this location here. So like we talked about in class, we require a half-inch airspace around the end of the beam to prevent capillary action from rotting the wood. So we want to get airflow through there, right? So if we have an airspace around, we end up getting a chance for it to dry out and not rot. So we want a half-inch airspace there. Okay. Location and placement of nails. Okay, so location of nails at the end of a beam, just trying to make that a little bit clearer. But so again, B is what we're talking about, right? So they're showing there where's the first set of nails located, and that is 4 to 6 inches from the end of a beam. So where does that come from? That comes from the code. It also comes from the span book. So if we go to the span book at the end, right? So if we're looking at the span book, again, the yellow is metric. The blue there is imperial. So beam starts right here. Built-up beams is probably about there somewhere. I think I went a little too far, but so around 405 is where I want to be. So at the end of built-up floor beams, right? So built-up floor beams is kind of what we're talking about. If we go to the very end of that section, which is on page 405. We have some notes there, and then there's also that drawing, right? So there's that drawing at the top. There's the notes here for end bearing of beams, 1 floor, 2 floor, and 3 floor. This is kind of what we were looking at today on one of the slides there at the beginning of class. So the 4 to 6 inches is coming right from here, right? So it's a 100 millimeter end distance. So if we have 100 millimeters, to convert that, we just divide that by 25.4. So if I have 100 millimeters in my calculator and I divide that by 25.4, that gives me 3.937 inches. So I'll just jot that down quick here. So 3.937 inches, right? So remembering that 25.4 millimeters is equal to 1 inch, right? So if the code tells me it's 100 millimeters, I divide that by 25.4, and then that gives me an answer in inches, which is what we have right here. So that ends up being 3. So if I subtract the 3 out of the calculator, I'm then left with fractions of an inch. I can multiply that by 16, which then tells me 14/16, but that's 5 or higher, so I have to round that to 15/16. So that's where the 4 and 6 inch come from, the 100 millimeters, okay? So there's a range there, right? So we can have that first set of nails in that range. Put that off to the side there. So 4 and 6 inches is what I'm looking for there, okay? Minimum beam bearing, okay? So again, we define that in the span book. Okay, so I got to go back to the span book, locate where that would be. So it's going to be located at the end of the built-up floor beam section. So which ends up for the new version being on page 406. So required bearing length. So if we kind of look at the drawing there, so we're told first of all that this was a bungalow, right? So 3-ply built-up beam, 24 by 40 bungalow. So that means it's 1 story, okay, supporting 1 floor. Something else that we need to know before we get the end bearing is the supported length, which is up here. So if the width of the building is 24, I take half of that, and that gives me my supported length. So if we did a quick little sketch up here of the building itself, right, our building is 24 feet wide, and it is 40 feet long. The beam is going down the middle here, okay? So when you're looking at supported length, you're looking at the floor joist. How much weight is bearing down on the beam? So I look at the 24-foot direction, divide that by 2. That gives me 12 feet of supported length bearing down on that beam. So if we go back and read through, we might see the word supported length there, right? So it's a bungalow, so we're dealing with one floor, so beams supporting one floor. So it says 3-ply beams with supported lengths greater than 14 feet require 4.5 inches of bearing. All other beams require 3 inches of bearing. So in this case, it is a 3-ply beam with supported lengths greater than 14 feet, sorry. Our supported length is only 12, not 14. So if it was 14 feet, or greater than 14 feet, so if it was greater than 14 feet, the bearing would have to be 4.5 inches. But in this case, it's not, so all other beams are 3 inches. So we can write down 3 inches there. Okay? So put that book off to the side for a little bit. Number, length, and spacing of nails. So that, again, oh, it's so unclear. So number, length, and spacing of nails, again, comes from the span book, right? So we know from our example, we wrote down 2 rows of 3.5 inch nails at 18 inch on center. Okay? So if we look at the span book, we can see right here they're kind of referring to the nail location. So if you look at that leader line, it tells us 450 millimeter nail spacing. We can see that it shows 2 rows of nails there. It doesn't really say 2 rows. It does say 2 rows in the code book. So we're just going to kind of take that for granted. It also says down here the length of the nail. Minimum nail penetration into the second member is 8 times the nail diameter. So you got to go the thickness of one material plus it has to go into the second component 8 times the nail diameter, which then equals 3.5 inches. Okay, is the minimum size nail. So that's why we go 2 rows of 3.5 inch nails, 18 inch on center, which is basically 450 mils. So if we just verify that, it's pretty close. It's a little less, but the same kind of a sequence that we did here, right? We divide that by 25.4, and that's going to give us an answer in inches. Okay, so we go 450 divided by 25.4, whoops, gives us 17.7165. So 17, so I'll just subtract the 17 there, so because I wrote it down, I have fractions of it in there, so I'll multiply that by 16, which then gives me the numerator. If that's 5 or higher, I have to round. So it's quite a bit lower than 18 inches, but it's something that's always been accepted. So that's in reality, if we're going by the 450, but acceptable is 18 inches, okay? It's okay to use the 18 inches. So we put that off to the side as well. Keep on going here. So E, now we can kind of look at the drawing there again. So E is basically telling you the distance from inside a foundation to inside a foundation. Okay? We know that outside a foundation to outside is 40 feet. Okay? So if we want to find the inside, we basically have to go 40 feet minus the thickness of the foundation here, which is 8 inches, minus the thickness of that foundation, which is also 8 inches, and that'll give us E, the inside dimension. So what I'm going to do there is I'm going to go 40 feet minus 8 inches twice. I'll try and show as much work on here as I can. So that's kind of what we did in class, right? So 40 feet minus 8, or you could say 40 feet minus 16 inches, or you could say 40 feet minus 1 foot 4. Basically all means the same thing. Whatever you want to do there. So I like to get, like I said in class, go 40 feet minus 1 foot 4, because it's easier on the brain. You basically just take away 2 feet and then kind of what's left over. Okay? So we end up with 38 foot 8. Okay? Now if we go ahead and just do maybe the math now in inches, I said it's probably a good idea to kind of do several different ways, so if we make a mistake we can kind of catch that. So I'm going to put 40 feet into inches, so I take 40 feet, I multiply by 12, that puts it into inches, so I have 480 inches. I'm going to subtract 16 inches, right, 8 and 8, which gives me 464. So that should be the answer there. So that's doing it in inches. That was doing it in feet and inches. Now I'm just going to make sure that the 38 foot 8 actually equals 464. So I'm going to go 38 times 12, which gives me the inch equivalent. I'm going to add on 8 now. And then they're both 464. So they both equal 464. Let's put a little check there that I double checked that. Mental note that that's been checked 2 different ways. Okay. So I can maybe go down to my drawing here and then label that. So the inside to inside dimension is now 38 foot 8 inches. Okay. Next thing that I could do there is get the length of the beam. So now I know the distance from inside a foundation to inside a foundation. So to get the length of the beam, I just have to include the bearing here and the bearing there. Okay. So was C labeled here? Yeah, I guess it was, right? C is actually here. Minimum bearing, 3 inches. So there's a little extension line here that says that that's 3 inches. And we also know that that's 3 inches there as well. The minimum bearing. So if I were to take E, which is 38 foot 8, then add 3 inches to it, and then add 3 inches to it, that would give me the length of the beam. So instead of having a formula written down there, right, I could write down inside dimension plus bearing times 2 in brackets. I find sometimes formulas are harder to memorize. If we just look at the picture, we know from inside to inside is 38 foot 8. Add 3 there, add 3 there. That's sometimes easier than a bunch of words, okay, for long-term memory, okay. So length of beam, I'm just simply going to take the inside measurement, which is 38 foot 8. And then I'm going to add on to that 3 inches twice. So I'm going to show everything there. I could kind of group things together to simplify things, but for a first example, we're basically taking inside measurement plus bearing plus bearing. Right, so that's the inside measurement plus 3 inches there plus 3 inches there. That's why I have all that written down there. So we're basically adding 6 inches onto the 38 foot 8. So if I just kind of work through that just by looking at those numbers, 6 inches from here jumped onto there is going to make that 39. So 4 inches got used, 2 are left over. So it's going to be 39 foot 2. Right, so that's 6 inches. I take 4 from here, plug it to that makes that 39. There was 2 inches left over. So now I'm also going to go ahead and do it in inches. So the answer of 38 foot 8 is also 464. So I'm going to put 464 in my calculator, and then I'm going to add on basically 6 inches there, which gives me 470. So again, I want to make sure that this number is actually equal to that number. So I'm going to go 39 times 12, add on 2 inches. That's correct. So that's double checked. Okay. So a little bit extra time, but not a ton there. Okay. So now what we have is the length of the beam, which is F. I can write that down right here. My length of beam actually stops right there. So that's F right here. So it stops here and here. So it includes that bearing. So that's actually 39 foot 2. So might as well write that down, right? It's going to help with visuals. Next thing is getting G, the clear span. Clear span. So we know from class that clear span goes from inside a foundation to inside a post. Inside a post to inside a post, and inside a post to inside a foundation. So we actually have 3 clear spans on this building. So to determine that, the easiest way I find to do it is there's more than one way, but the way that I like to do it is take the length of the beam and then remove all the bearing points. So a bearing point would be the 3 inches here, the 6-inch plate on the column. So that's not a 6-inch column, it's a 6-inch plate on the column. And then we have another 6-inch plate here that's bearing, and then we have another 3 inches over here. So that's all the bearing points located on that beam. So if I were to take the length of the beam, subtract the bearing points, 3, 6, 6, and 3, I'm then left with the total clear span of that beam. Now, if I then divide it by the number of locations where I have a clear span, I'll then get the individual clear span between supports. Okay, that's kind of how we're going to tackle that. So we're going to take the length of the beam, which is 470. So the length of the beam is 39 foot 2 or 470. And then we're going to subtract 3 inches here, which is the bearing, We're then going to subtract the plate, which is 6 inches. We're going to subtract this plate here, which is also 6 inches. And we're going to subtract the bearing at the far end. Once you get more comfortable, you can obviously speed this stuff up there, but I just kind of want to show everything there. So that's taking care of getting rid of the bearing points. In the brackets would actually give me the answer for the total clear span. So then I want to follow with dividing by the number of spaces. So that's not a constant. In this case, there's 3 spaces. If I had 3 posts, I would have 4 spaces. So in this, I would then divide by 4. But in this case, there's 2 posts, 3 spaces. Therefore, I divide by 3. Okay. So I can then plug those numbers in the calculator. So I already have the 470 there. I'll go minus 3, minus 6, minus 6, minus 3. Press equals, and I'll divide that by 3. So that gives me 150.66 repeating inches, which is 150 and, so we'll just subtract the 150 out of the calculator. We're left with decimals there, so multiply that by 16 to find a numerator. That's the numerator, but if that's 5 or higher, I get it rounded up, so I get it rounded to 11/16. Or I could also write down the foot, inches, and then fractions. So if I had 150.66666, I would divide that by 12. So that gives me 12 feet. Then I can go ahead and minus the 12 feet. I'm left with decimal feet there, so I multiply by 12, which then gives me 6 inches. So subtract the 6, left with fractions of an inch, multiply that by 16. That gives me 11/16. So one of those is all you really need. Probably a good practice tool to play around with both of them. So what that basically means is, so I'm going to stick with the inches there. That means that I have 150, I'll leave that decimal 0.66 there. So I have 150.66 here as well. Repeating inches, and then another 150.66 repeating inches there as well. Okay? So the clear span in 3 locations, all at 150 and 11/16. Okay? The next step is breaking up into quarter points. Okay, so where can we put the joints, right? We're allowed to place a joint on a beam at a quarter point. So if I just quickly by eye find the middle, so that's the clear span. If I take the clear span and divide it into 4 parts, I'd have a line, little line there, another little line there, and another little line there. That's kind of our next step, is finding H. Right, so H would be the distance from here to here. Okay, so it's a quarter of the clear span. A quarter of the clear span. So take that number basically, divide it by 4. It'll tell us what that distance is. So it's always dividing by 4 here. So we take the clear span, which is 150.66 repeating inches, and then we divide that by 4. Okay, and that'll give us our quarter point. So 150.6666, we divide that by 4, that gives us 37.666 repeating inches. So that equals 37 and 11/16. So if I subtract the 37, I'm left with a fraction. Multiply that by 16. So it gives me 10/16, but that's 5 or higher, so I make it 11/16. Or that could also be 3 foot, which is 36 inches. They're 1 inch left over. So 3 foot 1 and 11. Okay. The width of the column footing, we could do that right away. I guess it's on a video, so I'm not really wasting any time there. Maybe I don't know if I don't have the code book here. I actually left it at the college. It's a bungalow though, so I know that the number for so yeah, we'll go through it. We have, you can always skip through it, I guess, if you didn't want to look at this whenever you're actually going through it. But so basically, I'm not going to go through the entire thing, but just out of memory there, I'm kind of going by these numbers. But if it's a 1-story house, so column footings, right? So they're in the code book. There's a chart there that tells you the area of a column footing, right? So the area is basically the top of the column footing. So if I had a little sketch here of a column footing, So the area is the section on the top here, obviously, of that column footing. So there'd be a metal plate there, and then there'd be a post that's underneath the beam, right? So there's weight bearing down from the beam through the column post onto the column footing. So for a one-story building, the area of the footing is 4.3 feet squared. For a two-story building, it's 8.1 feet squared. And then for a three-story, I believe it's 10.8. So I might be off on these numbers. This one for sure, I know I'm correct. These two, I could be off a touch there. But we'll go over that whenever we get to foundations there. But while it's there, we got a video here. Might be a good opportunity to kind of show that as well, okay? So basically what we're dealing with here is a bungalow. So that means that the area of the footings for this building have to be 4.3 feet squared. But in the code book, it says that these numbers are only good up to basically 10 feet. So basically the distance in between, the distance from outside of foundation to the center of the building are only basically good up to 10 feet. If it exceeds 10 feet, you have to increase 10% for every foot that is increased beyond 10 feet. Okay? So it's not the clear span we look at there, it's the on-center spacing. So kind of what we have to do there is take the length of the building, which is 40 feet, and if we divide it by 3 spaces, there, so 40 divided by 3 gives us 13.333 repeating feet. Okay, so that's actually the on-center spacing. And that's telling us how much weight is being transferred from the foundation, and so all that distance, right, from the center of the column all the way to the outside of the foundation, that much weight is bearing down on that footing. And we have the same thing over here. We have the same amount of distance over here bearing down halfway here and halfway here. So it's kind of split, sharing that load. So code is good up to 10 feet for this number. If we go beyond 10 feet, we have to increase the number by 10% for every foot. So if we have 10 feet here, that means we've gone over by 3.333 feet. So should be then an increase of 10%. So if we move that decimal one location, right, or if you're going to multiply that, you would go 0.03, right? So we move that decimal place one location, and then that'll give us so only one location, so it should be a point right here. So 0.33333. So we just move, because we're going 10%, there's 1 0 there, so we shift that decimal one location, and then that's what we're going to use for our calculations. So we're going to take the area of 4.3. It has to be increased to make it to be larger, so we're going to throw a 1 in front, right? So the increase is 0.333, but we want to include the original number. So that's why I'm going to throw a 1 in front of that, so 1.33, and that should give us an increase there for the area. So if I go 4.3 times 1.33333, that gives us a new area of 5.73319 feet squared. So there was an increase of 3.333 feet. We got to add 10% for every foot. So we just moved the decimal place one location, right? So it started off as 3.333, so we just shifted the decimal over one spot. So it ended up being 0.3333. The reason why I threw a 1 in front is because the 1 includes the 4.3. If I didn't put the 1 here, I'd have the increase here, but I still have to add on the old area. So by having the 1, it takes care of adding that to the increase, okay? So hopefully that makes sense. That's the new area. Okay, so basically the area of the column footing for this building has to be 5.73 square feet. Okay? So then what I have to try and do is to try and determine these two dimensions here, which we could basically call that one the length, and we can call that one the width. They're going to be the same because it's the column footing, but I need to find two dimensions. So if I have area is created by having two dimensions. So I could take the area of 5.73 basically, and to find two dimensions, I just square root it. So if I square root the area, I'm going to end up with basically two numbers multiplied by themselves will give us that area. So it's exactly what we're looking for. Right? So if I square root this number, so I already have the number in the calculator, if I just press the square root button, then equals, it gives me 2.3944 feet. So basically what we just determined is that that is 2.3944 feet, and that's also 2.3944 feet. So we might want to take that and put it into inches, so I'll just multiply it by 12 to put it into inches. So times 12 gives me 28.73 inches. And then maybe I'll just write that down as a fraction. So I'll subtract the 28 out of the calculator. Left with my fraction, so multiply that by 16. I get my numerator. If that's 5 or higher, I got to round it up, so it ends up being 12/16, which then has to be reduced to 3/4. So divide that by 4, divide that by 4. There's my answer, 28 3/4. So that means L is equal to 28 3/4. That means W is equal to 28 3/4. Now there's a rule that we will talk about when we get into footings and foundations, but there's a rule in the code book that states that projection I guess maybe I wrote that down wrong there, but if it's actually thickness, so thickness is equal to or greater than, so the symbol is basically like this here, so equal or greater to projection. So I think in one of the books that we actually use, they have this backwards, but so the thickness is what we need to determine now, right? We know that the width and the length are both 28 3/4, but we don't know the thickness, right? So the thickness is equal to the projection. So what is the projection? The projection is how far does a footing extend beyond its support, okay? So that distance from there to there is P, projection. So how are we going to determine that? Well, we have all the information to determine that. If we look at our plan there, we see we have a 6-inch plate, not a column, a 6-inch plate. So that means that this plate here is 6 inches. We know that the distance from this corner to that corner of the footing is 28 3/4. So if we were to go 28 3/4 minus 6 inches, and we divide it by 2 because there's 2 projections, we'll then know that distance. Once we know that distance, the thickness has to be equal to that or greater. Okay? So to get the projection, I'm just going to maybe go to the top of the paper here. There's enough room. So to get the projection, if we're writing down a formula there, we take the column width, so column width, and then we subtract the plate, and then we divide that by 2. So the column width in this case is 28.75 minus the plate, which is 6 inches, and then we divide that by 2. So 28.75 minus 6 divided by 2. That gives us 11.375. So that would be 11, and so it's 3/8 there, but if we didn't know it was 3/8, we'd go minus 11 and multiply that by 16. So it tells us that the numerator is 6, your denominator is what you multiplied by, and then we'd have to reduce that because that's not the lowest term. So we divide the top by 2, and then divide the bottom by 2. So we'd have 11 3/8. Okay? So that would be the thickness. and the projection. So the projection would be 11 3/8, and the thickness would also be the same. So we now know the size of that column footing. It's 28 3/4 by 28 3/4, and it's 11 3/8 thick. Okay. The basement slab gets poured on top of that, right? So you got to make sure that it's in the proper elevation. So one of the biggest problems with that on this job, you can see that the column footing is much larger. So they actually have to excavate a little bit deeper at those locations. The top of the footings line up, right? You got to go deeper into the ground. So the footing on the outside, which is called a strip footing, is probably more than likely 8 inches thick. This one over here is 11 3/8 thick. So it's 3 3/8 deeper. So you have to excavate a little bit deeper there to get that to work out. So you can see on the paper, it actually says column footing area. We could write down the answer here, 5.73. We could also write down the width of the footing, which is 28 3/4. And then the thickness is over here, 11 3/8. So we can plug in our numbers there. So not enough room, obviously, for I and J to be showing all the work there, but that's why we got this, right? So you can take a look at that when time comes to it. So I'm just going to write down those answers, though. So the width of the column footing is 28 3/4. And the projection and thickness is 11 3/8. So quite a bit of work there. I don't expect that on an assignment until we've covered it. So, but I just figured while we're making the video, get that kind of out of the way. Okay. So if we keep on going here, I think I got all that labeled there now. I never labeled this here, so 1/4 point is 37. 37 11/16. So we have another 37 there and 11/16. Another 37 and 11. And one last time. Okay. Maybe we'll have a look in the span book to find what kind of material we're going to use here, right? So it's 3 2x-somethings. If you remember in class, that number changed to 5, right? Because we couldn't find it. Well, let's try to find it first, okay? So it's a bungalow, so it's 1 story. We know our supported length is 12 feet. So we're going to go under the span book, under built-up floor beam supporting 1 floor. So I got to go this direction. So 2 floors, no, 1 floor. So built-up floor beam supporting 1 floor. And we're looking at 3 plies. So let's start right at the beginning to prove that that's not going to work. So built-up floor beams, right? So always check these items when you're in the span book. Every time. Built-up floor beam, 1 floor, because it's a bungalow. Spruce pine fir, we use number 1, number 2. And then we have to follow our supported length, which is basically half of the width. So it's a 24-foot wide building, so therefore it's 12-foot supported length. So we follow that until we look for a 3-ply. So we're looking for a 3-ply that's going to support 12-foot 6 and 11/16. Right, so we're looking for a 3-ply that I'll be able to span at least 12-foot 6 and 11/16. So 12-foot 6 and 11/16 is what we're aiming for. Go to the 12, look under a 3-ply. That's 6'8", that won't work. Here's another 3-ply, 8'8", that won't work. Right, we need 12-foot 6 and 11. So if I keep on going, so those weren't big enough. So I'm still on 1 floor, Douglas fir, hem fir. So there's our spruce pine fir. Okay, so again, check the headings, built-up floor beam, 1 floor, spruce pine fir, number 1, number 2, support length is still 12. We look under the 3-ply 2x10, it'll span 10'7". We look at the 3-ply 2x12, it'll span 12'3". That won't work either. So that's not going to happen for us, right? So what we have to do is come up with a solution, okay? So we have to change that. So I think in class we decided to put 5 here, 5-ply, and we decided to go 2x10s instead of 2x12s. One of the reasons was because it's the smallest, so it's the minimum. So if you look at a 5-ply 2x10 beam, it's 13'4" span. If we looked at a 4-ply 2x12 beam, it's 14 foot 2. So there's quite a bit of overkill there. Either one would work, but keeping in mind what we talked about in class, you always want to try and minimize the size of that beam if you possibly can to keep headroom in the basement so you don't have to cut down your doors. Like if you go to finish a basement, your beam is low, it's going to have to be boxed in with drywall, that could actually force you to have to cut your doors, makes your rooms feel a lot smaller. So by going with a 5-ply 2x10, we're using a little bit more material, but they're probably cheaper to buy. So in the end, they're probably the same cost. We're just trying to maximize the headroom. I'm also a big believer in sometimes overkilling something is not the end of the world. Right? So if we went to 14 foot 2, we'd have a strong beam, but we're losing headroom. So we kind of got to split in the middle there. So we're trying to achieve 12 foot 6. We're hitting 13 foot 4. That's quite a bit more, almost a foot more. So I'd be happy with that. Okay, so we're going to go with 5-ply 2x10. The max span is the number we see right here, 13 foot 4. And that's kind of what we're going to go with. So everything changed. So that could be a drastic change depending on the building, right? That could change the bearing, like we talked about in class. Right, all of a sudden, we went from a 3-ply to a 5-ply. That changes the options at the back. So if we just take a quick peek there on 405 to see if anything changed. So if we read through, so we're still one floor, right? So beams supporting one floor. So now it says 3-ply beams with support length greater than 14 feet require 4.5. That didn't apply to us before because we only have a 12-foot supported length, but we were a 3-ply. So if that building would have been wider, that would have changed, right? So if we would have had a building with support length greater than 14 feet and being a 3-ply, it was 4.5. But if we change it to a 5-ply beam, which we just did, it says all other beams require 3-inch bearing. But in our case, nothing changes. But if something does change or you make a change, you need to go back and revise and see if that change changed something else at the beginning. Okay? So it doesn't affect anything dealing with the bearing. Okay? So we're basically ready to go ahead and start playing around with that beam there now. So I'm going to try and do the drawing on here as well. So I think in class I started off by maybe labeling the layers. So that's L1, that's L2, and then that's L3. Okay? So I'm going to start off by putting my joint over the column on the center ply, which is L2. I'm just going to put a joint right there. And do the same thing over here. So just for ease of construction, I have those joints on the middle plies resting right on top of columns. Okay. Then what I'm going to do is I'm actually going to place my quarter points to the left of the columns on layer 1. So I'm going to work on layer 1. I'm just going to quickly, just by eye, put little marks there to kind of indicate where the quarter points are for that clear span. I'll do the same thing here. That's roughly center. Probably about there. Just by eye. I'm not going to measure. It's just a visual key. So I want to place the quarter point on the left of the column. So I can never use the middle one. I can never use the one close to the foundation wall. I'm allowed to use the one close to column. Again, I can use the one close to the column. I can never use the middle span. I can use the one close to the column. I can use the one close to a column. Never the middle span. Never close to a foundation wall. So I chose to go to the left in class, right, when we did our example. So I'm going to take that joint and try to reference it up here. So that's actually a bird's eye view looking down on the beam there. So I took that joint and jumped it up to there. So on layer 1, if I'm on the left side of the column, I'm going to maintain that. So I have another quarter point here, so I'm going to put that right here. So maintain to try and get that step pattern. On layer 3, I'm going to throw my quarter point joint on the right. So there it is there. I'm going to try and eyeball that. So if I went to the right of the column on layer 3, stick to the right of the column on layer 3 to make math easy. You create that step pattern, which makes the calculations a lot easier. Okay? And even to build easier. Okay? So I'm going to go ahead and I'm going to label. I'll go ahead and label my beam. So I'm going to call this one here A. This one here is going to be B. And the far one over here is going to be C. Layer 3 is actually identical to layer 1, so let's take care of that one right away, but it's just flipped, right? A is the short one over here. Well, the short one's over there, so I'm going to write A over here. There's my B, and then there's C. Layer 2 could be slightly different. It ends up being the same here, but I'm not going to take a chance, so I'm going to label that one there as D. And then the middle one is going to still be B, and the far one will also be D. So these two here should be the same, okay? And then from there, we're ready to start working on the math, okay? Getting the actual components, component lengths. So I'm going to start off with layer 1 here. I'm going to have, which is also going to be layer 3. So layer 1 has piece A, piece B, and piece C, okay? So what I'm going to do is I'm going to look at piece A, which is right here. Stops here and stops here. I'm going to work from the left to the right, looking at everything that's involved in it. So I know that the distance from here, so the bearing basically here, is 3 inches. That's the first part of my math. Right, so we basically go from here to here, which is 3 inches. And then from there we add on 3 quarter points. There's 1 quarter point, 2 quarter points, 3 quarter points. We know that the quarter point distance is 37 11/16. So in reality, there's a 37 11/16 jump there, another 37 11/16 jump there, and another 37 11/16 jump there. So what I could do is I could go 37 11/16 times 3, or I could just do the long way, show the visual work of that actually happening. So 37, probably decimal form there would be better. And then I'm going to tally that up. Okay, so grab my calculator, 3 plus 37.666 plus 37.666 plus 37.666. This equals, I end up with 115.998, which basically rounds up to 116. Right, if we were to continue this, so I actually subtracted the 115 here. That's my fraction, so I multiply by 16. It tells me that's 15/16, but that's 5 or higher, so I round it to 16/16, which then makes it a whole number. So 16's, 1 and 1/16. So 116, okay? So if we were to put that in feet and inches, right, 9 feet is 108. So there's 8 inches left over. So I'll just write that down so I know that I'm going to have to buy a 10-footer for that. B now, the easiest way to calculate B is to look at the one that's sitting on top of the columns. Okay? So we know that the distance between the columns is 150.66. We know that the plate is 6 inches. So that B is resting on top of that column 3 inches on this side and 3 inches on that side. So for B, we could go 3 inches, which is basically starting from here. So 3 inches brings us to here. Then we'll go plus 150.66, which brings us to here. And then we have to add on 3 inches there. That'll give us the length of that. That's probably the easiest way, is to look at that middle ply. So 3 plus 150.66 plus 3 equals 156.66 inches, which is basically 156 11/16, or 13 foot 11/16. Okay? C now is basically at the far end there. I'm going to start from the right side now and work towards the left, since we know the bearing. Okay? So we know that there's 3 inches of bearing at the end here, which brings us to here. Right? If we draw a line there. And then from there we have a clear span, a full clear span. So instead of going 3711 plus 3711 plus 3711 plus 3711, I know that distance is 150.66, so I'll go plus 150.66 inches. And then we run into the plates. We can't forget to include that because it continues, right? C goes from all here all the way to here. So we've included 3 inches, we went 150. Now we have to include the 6-inch plate. And then we have to include 1 quarter point. So 37, so plus 37.666 inches. And that'll give us the length of piece C, okay? So we add that up. So we're going to go 3 plus 150.66 plus 6 inches plus 37.66. That gives us 197 there, 0.326. So 197, so let's subtract that out of the calculator. Left with the decimal, multiply that by 16 to get the numerator, so that's 5/16. Right? That's the numerator, that's your denominator. Then I reduce it to lowest terms. I put it into feet and inches. 192 is 16 feet, which means there's 5 inches left over. So that gives me basically my answer there, okay? So again, like I was saying in class, quarter point joints could be shifted plus or minus 6 inches because of, to allow for this kind of a thing, right? So in class, I didn't really want to say too much about that because it's your first time through, but what I could do is I could take this 5 inches and 5/16 and throw that onto another component. Like this one here is 13 foot, 11/16. We're going to buy a 14 footer there. So there's basically 11 inches, 11 and 5/16 of waste. So what I could do is take 5 and 5/16, throw it onto this one, and then I could then just buy a 16 footer here. So that's something that we can do. We can move a quarter point location plus or minus 6 inches for that kind of a thing. Because I don't want, and I'd have to buy an 18 footer here, right? So that's what we did in class. We just kept it with 18 feet, but in reality, I could take 5 and 5/16 added to that, which would then make that 13 foot 6 basically, right? So I could scrap that, put that at 13 foot 6, scrap that, and then put that at 16 feet. So the key is that all these three numbers have to equal the length of the beam. Length of the beam is 470. Right, so 13 foot 6 is the same as 160, so 156 basically plus 162. So if I added the 116 to the 162 and to 192, they should equal 470, okay? So 116 plus 162 plus 192 equals 470. So I just, for this example, since we've already done one, I just fudged those numbers because I'm allowed to, plus or minus 6 inches. Then I don't have to buy an 18 footer now. Now I can buy a 16 footer. I took the 5 and 5/16 and I brought it to B, right, for that one location. And then that'll make life easier. Okay, I'm not wasting material there. So the last thing I got to do is do layer 2. Maybe I'll do layer 2 at the top here. Layer 2 should have room there. It shouldn't take too long because we already have some of the numbers there. So layer 2 is basically D, B, and D. Okay, so D, B, and D. So if I start from the left, same idea. First thing is the bearing. Right, D starts here, so there's 3 inches of bearing, and then there's a clear span of 150.66. And then there's half of a post, so another 3 inches. So that just ends up being coincidence, right? Normally, that's not going to be the same as that. Okay, just sometimes it ends up being lucky like that. So basically, D, B, and D are all going to be the same length. But that's not always the case. So I have it labeled differently because sometimes that happens. So 156.66 would be the answer there, which is 156 and 11/16, which is 13 foot 11/16. Okay, B is going to be the same. We already know what B is down here. So there's no sense in recreating the wheel there. So I'll just write down the answer, 156 and 11. And then D we just calculated. So again, let's not recreate the wheel. We already know the answer. The key is when I add the 3 of those together, that they equal 470 or close to it. Okay, there's rounding issues there usually, but if I go 156.666, let's put 3 decimals there, times 3, that's what I get, 469.998. So if you were to actually round that up, so if I went minus 469 and multiply that by 16, it's telling me it's 15/16, but that's 5 or higher, so I have to make it 16/16, which means the actual answer is 470, okay? Not 469 and 15/16. So that's good, right? That equals the length of the beam. So those numbers are correct. So now I can go ahead and plug those in to my cutting list, right? So I have my parts labeled here, so I'll follow with that. I'm going to write down A here. And how many A's do I have? I actually, we made this actually a 5-ply, so I'm just going to throw that in there right now. Probably going to, maybe I'll put it below. It should be a 5-ply, just so I get the right numbers there. So what I'd probably do is make the top one the same as this one, and then the bottom one same as that one. Okay, so probably not the same 100% layout as we did in class, but the same idea. So to label that would be an A here. I'm going to scratch that off, that's not good. That's B here, and then we have C here. So basically layer 4 is the same as layer 1. I'm just going to call this one here layer 0, because I kind of went backwards on it. But we have C over here on layer 0. We have B in the middle here. And then we have A at the far end here. Okay, so layer 1, layer 3, layer 4, and layer 0 are the same. The only one that's different is layer 2. Okay, so hopefully that's not confusing people, but if we needed 5 layers, right? 5 plies. So we got 1, 2, 3, 4, 5. That top one doesn't count there. So this one goes here actually, and that one goes there. So how many A's? We got 1, 2, 3, 4. Okay, so we have 4 A's. What are we buying? So we're buying 2 by 10. So I'm going to write down 2 by 10 by, not sure yet. So if you look at A, what's the length of A? It's 1/16 or 9'8". So that means I need to buy a 10-footer. So I need 4 pieces of 2 by 10, 10 feet, and we're going to cut them to 9'8". Now we'll get the B's here. You got to remember that we kind of fudged a couple B's here, right? So there's basically going to be 4 B's that are different. So maybe I'll call them B1 beside it there. So layer 1, layer 3, layer 4, and then layer 0 have a B that's kind of been modified. Instead of making it what we calculated, 13 foot 11/16, we took the 5 and 5/16 from here and we threw it onto here. So that's actually happening 4 times. Okay. So what we're cutting it to is 162 or 13'6". So we're going to get 2 by 10s by 14 feet. So that didn't really change our purchase length, but it changed our cutting lengths. So that's B1. Or maybe put a little B1 here. Now I'll just throw another one in there for B2, because in reality, if you actually count, we actually have 5 B's. So one of those B's is a little different, right? So B2, there's going to be one of those. So that's the B2 up here for L2. Okay? So one of those is going to be a 2 by 10. Its cutting length is going to be actually what we calculated. So 156. So we're not allowed to shift a joint on a column, right? It has to land on the column. We can't shift that one. So that's 156 and 11/16 or 13 foot 11/16. Then we hit C. C, we've got 1, 2, 3, 4 of those. We modified that, right? We modified that down here. All 4 are down here. So what we did is we're actually going to cut those at 192. That's where we're actually going to save some money. and also time, right? A special order 18 footer is going to take you a couple weeks to get that in. There's going to be a little bit more of a cost because it has to be shipped in. Sometimes, depending on the lumberyard, they might actually make you buy a full skid of it. So you're not going to bother doing that. So you have to modify it somehow. That's why they have that plus or minus 6 inches, right? That's why we were allowed to do that. Because of the plus or minus 6 inches. Right? We took 6 inches, almost, right? A little less than 6 inches and shifted it over. So we'd be buying their 2x10s by 16 feet and then not have to cut them unless they're a little bit longer than 16 feet, which they tend to be. That would be a 14 footer there. And then the last one we need there is D. So D, there's 2 of them, one here, one there. So 2 of those. They're still going to be 2x10s. And they're actually the same length, right, as B2. So 156 and 11/16. Or 13 foot, 11/16. So we have to buy 14 footers for that. Okay, and the double check that, like we talked about in class, was how many pieces do we need to build the beam? So we basically have 5 layers, so 5, and there's 3 pieces per layer. So 5 times 3, which is equal to 15 pieces. So we need 15 pieces to actually build. How many are we buying? So we have 8 there, plus 1 is 9, plus 4 is 13, plus 2 is 15. So we need to buy 15 pieces. We need 15 pieces. We're in the ballpark anyways, right? So it doesn't mean it's 100% correct, but we're getting the same amount of pieces that we actually need. Okay, so hopefully this helps. Probably a good idea to save that, download it, put it somewhere maybe, right? So when you go to study for other tests and stuff like that, it's available to you.